Welcome to part 4 of our introductory lecture on base R programming. In this part, we're going to talk about iteration. The simplest form of iteration in R is the for loop. Here's how it works. The basic syntax has the word for, followed by parentheses, and we have an expression inside the parentheses that says index in some atomic vector. So here, in is a keyword. Index is some index variable, and when I wrote some atomic vector, that's just a vector that we're going to be iterating over. As usual, we have a chunk of code, and it's enclosed in curly braces. So what this will do is it will run that chunk of code, and typically that's going to somehow involve the elements of this atomic vector. And the reason for using a for loop is somehow to do things over and over, or to iterate in some way. Here's a very simple example. For I in 1 to 3, print I squared. What this does is it goes through each of the values in 1 to 3, 1, 2, and 3, and it successively assigns those values to I. So the first time that we make our way through this for loop, I is set to 1, and we print out 1 squared. The second time, I is set to 2, we print out 2 squared. The third time, I is set to 3, we print out 3 squared, and then we're done. Every pass through the loop assigns the next value to this index. R will actually create this index variable if it doesn't exist and override it if it does. Here is an example. I'm going to create a vector I that contains some famous musicians you may have heard of. Now I'm going to carry out a for loop where I iterate over 1 and 2. And what happens? Well, first I is 1, I print 1 over 1. Next I is 2, I print 1 over 2. And when the loop is all finished, I'm going to type in I again. And what do you know? John, Paul, Ringo, and George are gone, and I is now equal to 2. The reason is that 2 was the last value that the for loop set I equal to. It really does successively change the value of I to take on each of the values one by one that appear in that atomic vector. So we've talked about scope in our earlier videos. Scope also matters for loops. So where exactly is this index variable being created? Well, it is created in the environment where the loop was called. So if that loop was called inside of a function, then that variable I lives inside of the function. So here's a new version of the example from the previous slide with John, Paul, Ringo, and George. This is a function with no arguments. I think I mentioned earlier that that's possible. So here's an example of a function with no arguments. It still does something, but it doesn't require any inputs from the user. This is just an encapsulation of the previous code on the last slide inside a function. And the reason that I'm doing this is to show you what happens when I call the function f. So here I am in line 9 of my code chunk calling it. No input arguments. What do I get? Well, I get 0.1, then I get 0.5, just as before. So we're actually stepping through the for loop. And now I'm going to type in I. This time, I get John, Paul, Ringo, and George. And the reason is that that variable I is actually local to the function. The instance of I should say, that's in the for loop, the one that takes on the values 1 and 2, lives inside of the function f. Whereas the vector I that I created, John, Paul, Ringo, and George, lives outside the function. So they have different scope. John, Paul, Ringo, and George are in the global environment, whereas I is only within the scope of that function f. A for loop can iterate over any type of atomic vector, and we can call the index variable anything we like. So here is a vector of some personnel from a past iteration of core ERM. And I'm going to loop over person in personnel, and then I'm going to print a greeting. So the first time we go through the loop, person will take on the value Anna. The next time it will take on the value Frank. The next time it will take on the value Inbar. And finally, it will take on the value Sam. Now, here is something that's really important to remember about for loops and is kind of related to this scope idea that I mentioned before. So let's take a look at the loop that's in lines 1 through 3 on the top of the slide. For I in 1 to 5, I squared. If you run this code, nothing will happen. So why not? Well, this I squared actually isn't being evaluated and displayed. And this is maybe a little bit confusing because normally if you were just to have, say, a variable that's equal to 1 and type I squared in the console, it would print out 1 squared, which is 1. But with a for loop, that doesn't actually happen. So if you want to get values out from a for loop, you either have to explicitly print them, like we did on the previous slides, or you have to store them somewhere for later access. Okay, so what I'm going to do now is I'm going to create an empty atomic vector to store my results. This is a really common pattern that we're going to use all the time in the course. Constructing an object with a bunch of slots and then filling in those objects, that object element by element. So squares is an empty vector with length 5. You can think of it as a box that has 5 compartments. And as we go through our for loop, we're going to individually put items in each of those compartments. So for I in 1 to 5, squares I gets I squared. The first time we go through this loop, we will set the first element of squares equal to 1 squared. That's because initially I is equal to 1. The second time, we will set the second element of squares to 2 squared. That's because I is equal to 2, and so on, all the way up to 5. The fifth time we pass through this loop, we will set the fifth element of squares equal to 5 squared. When we're all done, we now have a vector that's full of all the numbers that we wanted. If we type squares in the console, we will see the vector 1, 4, 9, 16, 25. Now, this is a kind of overly complicated way to obtain a vector of squares in R. We could have just raised the vector 1 to 5 to the power 2, but it serves to illustrate this a simplest possible example of filling in the elements in a vector. There are 2 different kinds of loops in R. First is the for loop, and next is the while loop. You should use a for loop when you know in advance how many iterations you're going to need. And you should use a while loop when you don't know in advance how many iterations you're going to need. So a while loop checks a logical condition, and it keeps repeating a certain block of code over and over until that condition evaluates to false. In other words, it keeps evaluating that chunk of code as long as the condition remains true. Here's an example. How many coin flips are needed to get our first head? Well, it's random, and we're going to discuss this later on in the course, although depending on what iteration of the course you're watching, it might not be week 3, as it says on the slide here. So you can ignore that first line, and I'm going to just define a vector of heads and tails. I'm doing that in line 7, and I'm using a command called sample that we haven't met yet, so don't worry too much about the syntax of that sample command. But basically what I've done here is I have set up a variable nflips that is equal to 0, and I have set a variable called coinflip that is initially equal to tails. I'm now going to check if the coin flip is equal to tails, identical coin flip tails, then the statement is true. I'm going to drop into this loop, and I'm going to carry out the steps that are in lines 7 and 8. Line 7 flips the coin, so it randomly chooses between heads and tails and assigns that value to coin flip. And then I'm going to increment my counter. So my counter is n flips. It starts at 0 because initially I haven't flipped the coin at all. And the first time I go through the while loop, I'm going to add 1 to it. Okay, so what happens then? Well, if I got a tails, then we'll go back up to line 6 and check, what is the value of coin flip? Hey, it's tails. I've got to drop into the loop again. I'm going to repeat the same thing. Each time I do this, I am incrementing the n flips counter. It's getting one bigger. But as soon as I get a heads, then I will visit line 6 and check, is coin flip equal to tails? I'll get false, and I will fall out of the loop. So this time, it actually took me 5 flips to get my first heads. This is, of course, random. So if you run this code, you might get a heads on your first flip, or it might take you more than 5 flips. But simulations are one common case when we don't necessarily know how many times we're going to have to repeat a certain series of steps. And a while loop is exactly the right solution when we find ourselves with a problem like that. Now, I've just spent quite a bit of time talking about loops, but actually in this course, we're typically going to avoid explicit loops. Loops are usually avoidable in R, and they are typically considered to be poor programming style. They're usually harder to debug. They can be harder to understand. If you're very used to writing loops in other languages, don't worry, you'll see many examples of how to think about this. But basically, vectorized functions and mathematical operations can replace lots and lots of loops. And then functional programming is an approach that we can use when we do need to explicitly iterate over some object. We can't just use vectorized function, but we want the bookkeeping to be cleaner. So with functional programming, there are still loops going on under the hood, but we don't write them explicitly. And we'll be talking about this in a future lecture. With all of that out of the way, it's still true that sometimes there's no way around writing a loop. A common complaint that you will hear is that loops in R are slow. Is this true? Well, kind of, but there are several caveats. First of all, it's rarely the case that the loop itself is the problem. More commonly, it's everything else that surrounds the loop or is contained inside it. For example, needless work that's carried out inside the loop, lots and lots of function calls that could be avoided. Here's a big one, making copies of objects that don't really need to be copied. And then also nested loop, where you have loops inside of loops inside of loops inside of loops. Some tips for writing faster code are as follows. First of all, if you're trying to fill up an object by looping over it, you should start by constructing that object and making it full of, say, NAs. This means that as you start to fill in the objects, R is not forced to copy that. So let's say it's a vector that you're filling up. R is not forced to copy it over and over and over. Those operations are very, very expensive. Second of all, quite often there are things that you can compute outside of the loop, things that aren't going to change over the iterations. But when we're not paying attention, we sometimes accidentally recompute those every time. Thinking about what can be computed outside of the loop and stored is a great way to speed up your loops. Another idea is to prefer vectorized functions and matrix operations to loops. Just because you can write something as a loop, that doesn't mean you should. If what you're really trying to do is equivalent to matrix multiplication, well, don't implement that by hand, just do matrix multiplication. We've had decades and decades of progress in numerical analysis. There are great algorithms for doing all the classic mathematical computations. They're built into R. So sometimes the way to avoid a loop is to just figure out that what you're trying to do is actually equivalent to some kind of matrix operation or some other mathematical function that's built in and that you can use without incurring all of the speed considerations that we've mentioned here. Okay, now, do you remember from earlier in this lecture, we compared two functions, get value and get value to. Both of these functions do exactly the same thing. They assign numeric values to chess pieces following a commonly used convention. But the first of these uses an overgrown if tree, which is my silly name for just a long, complicated if-else-if statement. The second uses what's called a lookup table, which is in many ways a much more elegant, although perhaps slightly more difficult to understand solution, at least the first time you've seen it. So we're going to use this as a case study to see how it's possible to write faster code. So what I'm going to do here is generate a character vector of 1 million chess pieces, and I'm going to do this at random. Again, we're going to talk about these 3 lines in a later week, possibly not week 3, depending on what year you're watching this. But for the moment, you can just ignore this, and line 2 is going to create a random vector full of these chess pieces, queen, rook, knight, bishop, pawn. And its size is 1 million in length. Okay, so here are 3 different methods that I can assign numeric values to my 1 million chess pieces. The first option is a for loop that repeatedly calls the function getValue, and it doesn't pre-allocate any memory to store the result. So this is the worst solution. It's going to be the slowest, and I don't recommend it. The second is a for loop that repeatedly calls that getValue function, but does pre-allocate memory to store the result. And the third is a fully vectorized solution that doesn't use loops or function calls. We've actually already written that solution. It's called getValue2. So let's take a look at how these 3 different options perform in practice. Method number 1, as I mentioned before, is going to use a for loop. So how will this work? I'm going to start off with my function. It's a function of x. I start off by creating an empty object results. That's what I do in line 2. Results gets null. So there's nothing there. It's just the empty set. Then I'm going to loop from 1 to the length of x. And each time I go through my for loop, I'm going to assign getValue of xi to results I. In other words, I'm going to take the ith element of my input vector x. I'm going to pass that into the function getValue, which returns the value of the chess piece. So let's say that I is 1, and let's say that the first chess piece in my list is queen. So then x of 1 is queen. My function getValue is evaluating queen, so it's going to return 9, and I will then assign the number 9 to the first element of results. I'll then set I as 2 and continue. When I'm all done, I will return the vector results, which has the numeric values of all the chess pieces. Method 2 is similar, but it involves pre-allocating in line 10 a vector that is the same length of x. So this means that R finds memory in the computer, it basically sets up a collection of memory locations that are all nicely arranged in a row and easy to access. And then we're going to use exactly the same looping logic as before. So the logic is the same. The only difference is that rather than initializing results to be the empty set, I initialize it to be a long vector with the appropriate length, the length of x. And that means that R already knows in advance how much memory it's going to be using. So it won't have to make copies of objects over and over. Method 3 doesn't actually need its own function because that's just getValue2. Let's take a look at how these different solutions perform. System time is a function you can use to time some command. So I'm now going to time the command results gets method 1 of chess pieces. So what this will do is it will take my 1 million chess pieces and it will apply method 1 to convert the names of the pieces to numeric values. It will then store that result in the vector results 1. So this takes a little under 1 second. Okay, so that's not terribly slow, but it's not terribly fast either. That's my first solution. My second solution is going to pre-allocate the vector to store the results. Now, it's not a huge speed up, but look how we've gone from about 0.85 seconds to 0.71, purely by pre-allocating memory, which is really easy. So in some sense, we're getting a speed up almost totally for free. Why not get it? So method 1 is pretty bad. Method 2 is slightly better. How about method 3? That's my lookup table. Method 3 takes, that looks like about 1/100th of a second. So method 3 is almost 100 times faster than method 1. Not quite, but close. Why is that? Well, there's no loops. It's much faster in R to use vectorized operations. It's not that loops are especially slow per se, it's that vectorized operations are incredibly fast. And that's what results 3 does. Results 3 is using my fully vectorized function, getValue2, that relies on a lookup table. The other thing about getValue2 to bear in mind is it doesn't make tons and tons of function calls. So both results 1 and results 2 were generated by repeatedly calling that getValue function. My getValue2 function is a single function call that can handle the whole vector in one fell swoop. And just in case you're worried, at the very bottom of the slide, I'm going to check to see that the results of these three methods all agree, and they do. Now we finally know enough R to do some mildly interesting things. So in this exercise, you're going to take a look at the well-known Fibonacci sequence and think about different ways that you could compute them in R. So, as usual, pause the video, work your way through these exercises, and check your work.